So on Monday, we derived one expression for the magnetic energy that is given by Wm equal to summation of k, phi k, I k, and there's 1/2 in front of it. 你如果嫌我字太难看的话，就看讲义。Well, you have to be careful about the physical meaning of all the variables inside. Phi k is the total flux going through the loop k, and Ik is basically the current running in loop k. Okay, and so imagine that you have a lot of loops in space. Well, suppose that this loop is so small in the atomic scale. 这个原子分子那么小，你要把这个加起来的话，这个 k 就大得不得了。So when the number of loops is huge, and this loop is very, very small, then you can do integration, right? So let's look at this phi k. Well, previously we know that the phi is equal to the cross-loop integration of A, the vector potential, over a path over the loop. So it's a cross-loop integration of the vector potential over the current loop. And I can also be expressed as an integration of your current density, volume current density, over some surface. Okay, so somehow this magnetic flux is connected to the vector potential, the magnetic field, and I is connected to, can be calculated from the distributed integration of the current density. Okay, so let's assume that this is a very, very shrink into some atomic scale with some volume. Then you notice that this, in fact, is a differential volume. Okay, so this integration can be converted into a volume integration. This is converted into a volume integration of this kind of expression, 1/2. Okay, so when you reduce the system to the current loop into a small atomic current loop, then this summation is converted into a volume integration of A dot J. But usually we don't work with A because A is something created to simplify the calculation. A was created to calculate the magnetic field. So somehow there's still one step to convert this into magnetic field that we are all familiar with. Okay, so somehow that's the dual conversion. And inside this expression, your J can be calculated from Ampere's law. Right, this is something you are familiar with. This is Ampere's law. 写黑板的话，速度就比较慢了。所以呢，我可能写快一点 ，right？ 但是一步一步的，你可以看到我怎么计算。所以呢，这个式子，我们给 Wm can be written into 1/2 and then A dot with curl of H dV. Well, then we have to think about how to convert this expression into a function of B and H alone without having this vector potential, because we are all familiar with H and B, but not quite familiar with A. A is a mathematical symbol for the purpose of some calculation. Okay, good. So let's do this. This is dot product. So let's calculate. Let's pick up one vector identity that is A cross H. This vector identity, well, this expression can be converted into two terms. One is what? One is curl of A dot H, because this is factor. If I'm wrong, you have to tell me. And then you have what? A dot curl of H, I believe. Right? Am I right? Right. So this is the formula you can pick it up from vector calculus. So with this, you start to create B field in this expression. Okay, now in this expression, you identify this term. Okay, you identify this term, and so now this A dot curl of H can be written into B dot H, and then you have a 1/2 in front of it and do the volume integration. And then you have second term. If you move this term to the left hand side, give it a plus sign, then you have this term minus this term. So you have divergence of A cross H. And again, this is volume integration. 到这里有没有问题？没问题 ，right？ 这只是一个这个计算的过程。I really don't want to spend much time on this. Okay, but this is why I use the Stokes theorem. No, I'm sorry. Use divergence theorem. You can convert this into a curved surface integration of A cross H, and then that with S. Now, you are dealing with field in all space. 所以这个 volume, 即使是你的这个 integration volume is small, but you are dealing with the field. The field can penetrate outside this volume, right? 即使你的 curl loop 是在这个物质里头，这个物质这么大，但是呢，当你在计算场的时候呢，这个场呢是不受这个物质的这个界面的限制，它是可以 extend 到无限大去。So the integration of the volume and the surface has to go to infinite. Okay, has to go to infinite. So if you think about this integration for a small dipole, a small current loop, this A is proportional to 1 over R squared. If you pick up the magnetic dipole field from your handout, you're going to see that this A in the far field is proportional to 1 over R squared, and this H is proportional to 1 over R cubed. And this surface is proportional to R squared. So very similar to the calculation for the electric energy, this integration has to be equal to 0, because 这个乘上这个，再乘上这个，然后让 R 趋向无限大 ，you get nothing for this surface integration. But even you have this integration, let this volume to go to infinite, this term is not going to be zero, because the integration is from a small point to everywhere in space. Even a differential integration at far away gives you nothing, but the integration here is going to give you some finite value. Okay, 所以即使这个体积让它变得无限大，这一项不会等于0，因为这积分是从里头一点一点把它积到这个无限大去。这里积分不等于0，外头积分可能会等于0 ，but that is fine. You have to keep this term. Okay, so as a result, you have the magnetic energy expressed by the field as a function of field. That is 1/2 B dot H dot V. Okay, and 1/2 B dot H can be written into mu, 1/2 of mu H squared, or equal to 1 over 2 permeability multiplied with B squared. And this is called the volume density of magnetic energy. 所以这是volume density of magnetic energy. And I want you to compare this with the electric energy. That is 1/2 E dot D equal to epsilon over 2 E squared equal to 1 over 2 epsilon D squared. So you see the symmetry between these two expressions. That will help you to remember it. Okay, but you have to know how to derive this and physically understand every step. Okay, 有没有问题？没问题 ，right？ 我想这个一步一步很清楚，都告诉你这个物理的来源是怎么样。Now, previously, you obtained inductance. That is equal to what? The energy for an inductor. Last time you also derived one expression. The magnetic energy in a piece of inductor is equal to 1/2 I phi. No, it's a single loop, so it's better to write down like Li squared. Right? 之前你有得到这么一个式子 associated with one inductor. 那这个呢？你现在又得到一个式子 ，this is equal to the volume integration of B dot H dV. So this means that you can always calculate the inductance from 2Wm, the stored energy inside the inductor, divided by I squared. So this will offer you another path to calculate the inductance of a piece of inductor. 那有时候呢，这个计算比这个之前你定义这个等于 magnetic linkage divided by I 还容易。This sometimes it's easier. OK， 我给你一个例子。在你们课本里头有一个例子 ，if you calculate this, if you calculate the inductance from this expression, it's very difficult to understand, but it's quite straightforward to calculate the inductance from this calculation. All right. So the example is that you have a piece of cylindrical conductor, and this is basically a piece of wire, and the current is running, say, along some direction, and return from outside. This example is the same as the one in midterm number 2. All right, so this is a piece of wire, cylindrical wire, with a radius, say, radius of A, and for the outer conductor, you have radius of B, and there's a uniform current inside this conductor. And you want to figure out the inductance of this piece of coaxial cable. 所以你注意到之前我们在算 transmission line 的时候呢，里头有几个重要参数。One is the inductance per unit length. So we want to calculate this, the inductance per unit length for this coaxial cable. Okay, and when you think about this, it's really difficult to calculate that from this expression. All right, because what is the magnetic linkage associated with this structure? It's hard to imagine, right? Because I don't have current loop. But let's calculate the magnetic energy. And so we need to figure out the magnetic field everywhere. And you have cylindrical symmetry associated with this problem. So you first create a loop right here. Use Ampere's law to calculate the magnetic field inside this piece of wire, right? So when R is less than A, you use Ampere's law. The current containing the current contained inside this small wire, small radius, is equal to this is along phi direction. This is equal to the total current multiplied with the ratio of the area. So you have pi r square pi a square. 因为它是一个 uniform current. Therefore, on the right-hand side, the current within this radius is going to be equal to the total current multiplied with the ratio of the surface area. 这里没问题, right? So you have the phi component of the magnetic field intensity equal to pi a square, 2 pi a square r. OK. 这是在第一个这个 r 小于 a 的范围之内是这个样子。But in the second region, if you pick up a circle between r less than a and larger than b, r larger than a and less than b, so in this region r larger than a less than b, on the right-hand side, this is going to be the total current. 所以呢，这里变成 h phi 2 pi r equal to I0. 没有问题，没有问题 ，right？ 天气会不会太冷？你如果觉得冷的话，我让你上来运动一下，写一写。你会觉得汗流浃背，有没有问题？没有问题 ，right? So this is the simple answer: h phi equal to I naught divided by 2 pi r. Now, let's calculate the total energy, magnetic energy stored inside the system. Well, of course, there's a trivial solution. For r larger than b, if we create a loop like this, the forward current is going to be cancelled by the backward current. So you get nothing outside this wire. Okay, so if we integrate over the whole volume in this expression, then you can deduce the magnetic energy stored inside the system. Okay, 这个 volume 呢？我们先算 B dot H, well basically this is 1/2 multiplied with the permeability, and then you have H squared. Okay, suppose that this is the non-magnetic material, a piece of wire using copper. Then copper is not a magnetic material, so this is mu naught. This is mu naught. OK， 所以呢，我们先算这个里头在导线里头的能量是多大，会等于 mu naught divided by 2, and then take square of this. You have 1/4 pi square r square a to the 4th power, and then integrate with the volume. 你这个 volume 呢，你可以在这里取一小圈。然后呢，取一个长度 ，let's call this L. So the small volume defined by this small cylindrical wire is going to be equal to dV equal to 2 pi r L dr. OK， 有没有问题？你先把这个面积乘出来是 2 pi r dr， 面积再乘以长度 给你小的这个体积大小。Okay, so we multiply this 2 pi r L dr and do an integration from 0 to a because we are calculating the magnetic energy inside the core of the coaxial cable. So we integrate this from 0 to a. And then there's a second term, integration from a to b, and again, you calculate 1/2 mu naught multiplied with h squared. So h is right here. So you have I naught squared to 4 pi square r squared. Again, the volume is a small volume is 2 pi r L dr. But when we when we did the calculation for this h phi, there's one thing missing. This is current. So we have to put this current back. 没有问题 right? 有2项，这一项是导线里头这个 core 里头的能量，这个是导线这个中心的这个导线的外头从这里到这里的能量。所以这个积分都很容易，我想我可以让你自己做，这个积分都很容易。那在这里呢，你记住这里是这个中心导线有带电流的这个能量 ，so let's call this Wm internal to the conductor, and let's call this Wm external to the current region. And each of this, Wm I, is going to be equal to 1/2 of L internal multiplied with I 0 squared. And then for the external energy outside the current will also give you an external inductance multiplied with the square of the current. So from this, you can calculate Li and Le, and the total inductance is going to be equal to Li plus Le, because you have a linear summation right here. OK, 那我们给这个一个称呼，这个叫做 internal inductance。我们给这个一个称呼叫做 external inductance。那所谓这里的定义 internal 或 external 是for the region containing I, and this external means that this is a region without I. 所以下回你如果看到这个名称 internal inductance, this means that you are calculating the inductance in the region where you don't have any, you have current, because the current is running inside the wire. And next time when you read external inductance, this means that you are reading the inductance associated with the region without any current. OK, 那这个从能量的观点上头来算的话，这个题目变得很简单。But if you go from the original definition, L equal to the magnetic linkage divided by I, then you have to find out the loops. Okay, so for material with continuous distribution, it's going to be difficult to find the loops for your calculation. 有没有问题？所以这是一个标准的例子，让你计算电感从这个能量的角度上头来算。好，我们来看另外一个例子，跟这能量没什么关系的但是这个例子很重要，叫做 Hall effect。OK， 这个 Hall effect 是什么 ？Well， 我们看a piece of material。Suppose that you send a current through this material. So you have a current, say this is J along some y direction, and you put this sample inside a magnetic field, say along some z direction. Okay. And microscopically, you have some charge carriers running inside this material. And if this is just a piece of metal, then you are sure that this is there are electrons moving inside this piece of metal. But if this is a piece of semiconductor, sometimes it's hard to see immediately what kind of charge carriers moving inside this piece of metal. So if we have some charge carriers, and it could be electrons or it could be holes. So this U could be some hole moving around y direction, or could be some electrons moving in the negative y direction. 来，它可能是电子或电动在里头跑。那电子电动呢，同一个电流方向，你可能同一个电流方向，电子电动的方向是互相相反的。那当这个电荷在里头跑的时候 ，say this is a positive charge running inside. Well, along this direction, it's going to be along x direction. If you have some holes running inside, then the force is equal to the magnetic force experienced by this charge. It's going to be equal to some charge, and then U cross with B. Okay. So if you calculate, if this is whole charge, then you have Q. Well, whatever charge, it could be positive, negative. If this is whole, then you have UH, AY cross with AZ, and this is B0. Right? So this gives you AX. So this means that you are going to have a force along x direction. This charge is going to be pushed along x direction if this is a whole charge. So you're going to have more positive potential on this side than this side. 你会有一个这个 induced voltage, and this is more positive than the electric potential on this side. Now, so this electric field is going to go this direction. Let's call this Hall field. Okay, this field at steady state, well, you're going to accumulate electric field. You're going to accumulate charges, whole charge on this side. Therefore, you create an electric field from here to here. This is going to against the motion of the hole to this direction, right? 因为你电场朝这个方向，你如果这里有这个正电荷的话，它会把正电荷推到这个方向来。所以呢，这两个力，电力跟磁力会抵消掉 QE plus QU cross B. Eventually, the electric force will be cancelled by the magnetic force. Okay, so you have E equal to minus U cross B, and let's call it label it like a Hall field. So this E of H is going to be equal to minus U H B0. For Halls, 如果是电动的话，但是呢，如果说这个是电子的话，这个变成 Q, take this, minus UE. Again, you do this cross product to get AX, and then this is B naught. So the force for electrons is going to be on the opposite direction, in the minus X direction. So for this Hall field, let's label this as HH for this H, and for this HE, this EH, this H is referred to the H of this person's name. The second label refers to the type of the charge. OK， 所以这个呢所代表的是 HOLE， 是电动。所以在这里呢，这是 Hall field， 这个叫做 Hall field。所以对这个来讲的话，你会给它一个，因为这个负号的关系，你会给它一个，再给它变成一个正号回来，变成 UEB0。好。This is very convenient to identify the type of charges inside this material, because if you have hole running inside this material, this side is going to be more positive than this side. If you have electrons moving inside this material, this side is going to be more negative than this side. 所以你只要量这两端的电压是正的还负的，比如说这里是正的还负的，你就知道这里头跑的是电子还是电动。Okay, so you find the first application of this device, this scheme. You can identify whether this is electrons or holes running inside. 那这个实验呢，不只告诉你这个讯息而已，我们再看一下，它还可以告诉你什么。来，我们把它给它这个 dimension. If you have a dimension, this is called A. If you have a dimension, this is called D. And this is called L, for example, right? 可能跟你里头的 label 不太一样。我们来看一下，这个你知道这个 Ga is equal to the volume charge density multiplied with U, right? And this is measurable. 可以量测的，从这里出来电流多少，你可以量它。 And you also know the U from this expression. Now you have U. If I don't worry about the sign, then my U is equal to the Hall field divided by the magnetic field. This can be measured. All right. Suppose that you have a Hall voltage between these two ends. You have a Hall voltage. This Hall voltage is going to be equal to the Hall field multiplied with L. 在你的讲义里头是 L 还是 D？ 我们把它弄得跟你讲义一样。在你讲义里头这个方向 A D， 所以呢，我们把它换过来。所以呢，在这里你的 Hall field multiplied with D is give you a Hall voltage. This can be measured, right? So this is equal to Hall voltage divided by D, and then divided by the magnetic field. 所以呢，这个可以量，这个可以量，所以 your charge density is equal to the current divided by U, that is VH multiplied with dB0. So you can calculate the charge density from this expression. OK， 所以给你一个半导体物质，你可以量里头的电荷密度了，还可以决定里头到底是电子还是电动在跑。Okay, so what else could we get? We sometimes will be interested in knowing the mobility of the material. And mobility was defined to be a ratio of the speed of the charge and also the electric field you apply to it. This is the external field you apply to it. So along this direction, you have an electric field you apply to it. That is equal to, suppose that you have a voltage, say you have a voltage, external voltage applied to it, and this is grounded. So this is equal to the external voltage divided by the length of the device. Right? So if you want to know the mobility of this charge, you can do this calculation. U divided by external. And this speed can be measured from this term. So you have VH dB0 divided by the external field. That is equal to L, and this is V external. You看这些微观的量，在这个实验里头一个一个算出来，所以你有一个式子算出这个电荷的 mobility. OK， 那你有的这些量之后呢，你就可以算它的 conductivity 了 ，right？ 你的 conductivity 是什么？Conductivity is equal to mobility multiplied with the volume charge density. So you multiply these two terms together to get your conductivity of this piece of semiconductor material. And this multiplication is quite simple. You first cancel out this. OK， 然后呢，你的这个计算很简单，基本上你就把这两个乘在一块。 然后在这里头，你有了 conductivity 之后，你可以 verify 一下 R equal to V external divided by I. This is equal to 1 over conductivity divided and the length of the device, which is L, divided by the surface area. So you have A multiplied with D here. OK， 所以呢，这个你可以从这些式子求出来，也可以直接量它的 V over I。OK， 所以这些微观的量，在我们介绍这个 Ohm's law 的时候呢 ，we talk about some microscopic variables, including mobility, charge density, conductivity. Now you can deduce those microscopic quantities from this single experiment. 单一个实验可以告诉你这么多的讯息。And it also tells you what kind of charge propagating inside. OK， 那这个叫做 Hall effect。那这个自从半导体发明之后，这个实验变得很重要。OK， 因为它告诉你里头到底是 P-type 的半导体还是 N-type 的半导体，是哪一种电荷在跑？有没有问题？没有 ，right？ 好，进入今天要教你的最后一个 topic。Suppose that you have a coil. Okay, and there's a current running inside. This current is supplied by some current source. Suppose that you have some material inside. Usually it's a magnetic material, and you want to pull it. If you want to pull it, you need to use some force to pull it, right? And want to know what would be this force. If you want to just pull it, given some current running inside from a power source. And last time we calculated the electric force based on virtual displacement. So think about that you pull this with a small distance. Now you have to do mechanical work this big. Some magnetic force, magnetic energy. And based on the energy conservation, you can write down the total energy supplied by this power source has to be equal to the work you do on this system plus the internal energy the change of the internal energy stored in this system based on if you have a constant current. OK， 你记得这个实验 ，right？ 如果说有一个这个 parallel plate capacitor， 然后呢，我如果把它接上一个 constant voltage 的一个power supply 的话，然后要拉它，我有同样的这个 power supplies energy has to be equal to the mechanical work you do on this system plus the change of the internal energy at constant voltage. OK， 所以呢，这个是类似的问题。那这个 mechanical force 已经告诉你是这个。然后呢，because you keep this system at a constant current, so you know a little bit change of this energy supplied by this source is going to be equal to the magnetic flux, the change of a little bit of magnetic flux. 你拉动这里的时候呢，这里的 magnetic flux 改变了，但是电流不变。So this is equal to I supplied by this current source multiplied with the small change of the magnetic flux in the system. Because this is set at a constant current. But if you have a small change of the magnetic flux in the system, the total change of the internal energy is going to be equal to 1/2 of constant current multiplied with the small change of the magnetic flux. OK， 所以呢，从这里你得到，这边是1乘以这个，这里是1/2乘以这个，所以你得到 1/2 I d phi or the same thing d w m constant current equal to dWm, the mechanical work you do to the system. And of course, this is equal to F dot dl. Okay, so based on these experiments, if you put a power source into the system, then you have this relationship. And this is a constant current experiment. And 从这个基本的 vector calculus， 你知道这个等于 divergence gradient of Wm constant current dot with dl。在你的教科书第2章的地方，告诉你说，一个变数的小改变，在空间里头相当于是 gradient of this dot with the displacement vector. So you have one formula, that is your mechanical force. You have to you have to pull the material in that system is equal to gradient of Wm constant current. 有没有问题？这个跟之前计算 electric force 的方法一模一样。Okay, and in practice, this energy Wm is equal to 1/2 Li squared. At the constant current, your gradient of Wm is equal to 1/2 I squared gradient of L. If you know your inductance, you can do this calculation. OK， 那这个是一个方法，一个实验。For the second experiment, suppose that you don't have this power supply. Then you remove this. Then you end up having a result that is the change of mechanical force, the change of mechanical energy, plus dW magnetic energy without a current. 这个没有这个power source 的话呢，里头的 magnetic flux 是维持一样的，因为 total energy 不会改变。你的 power supply 没有提供这个 energy， 所以呢，这个是相当于一个 constant flux 的 experiments。OK， 你把这个拿掉，想象它是一个这个实验呢，里头永远有个电流，但是你拉它的时候，这个电流会有改变，但是里头的 flux 维持不变。这种状况之下，你会得到右手边等于0， So your F dot dl is going to be equal to minus gradient of Wm constant phi. OK， 这两个的计算结果会是一样的，因为都是你想象出来的实验来计算你拉这个东西所需要花的力气。OK， 那在这种状况之下呢，这个 Wm 通常是从这个计算里头得到。OK， 因为你的这个 magnetic flux 基本上维持一定，在这种问题里头。Okay, so this is how you calculate the magnetic force you have to use to move something inside a magnetic system. 那这个计算基本上跟这个电力的计算是1对1的关系，你可以从那里呢得到相关的这个观念。Okay, good. So we'll come back on Saturday at 10:10 a.m. Okay, see you.